Hi, class. So this is our last lecture in chapter 16. We're going to cover chapter 16.4 today, and this is going to be on Gibbs free energy. And I've already started my screen share. So start this PowerPoint here. It's up. You'll need worksheets 24 and 25 for later in the lecture. We'll be going over those worksheets. So let me increase slideshow. Oh, there we go. So chapter 16.4, Gibbs free energy. We're going to define Gibbs free energy and describe its relation to spontaneity. We're going to calculate free energy changes for processes, mainly chemical reactions, using free energies of formation for reactants and products. And you have to remember, this is what we've done previously for enthalpy and entropy. And now we're going to apply Hess's law to free energy calculations for reactions. We're also going to calculate free energy change for a process using enthalpies of formation and entropies of formation. That'll be in worksheet 24. We'll relate the standard free energy changes to equilibrium constants, which we studied previously in our previous unit. It was all about equilibrium. And then lastly, we'll explain how temperature affects the spontaneity of some processes. So there's a temperature variable in our free energy equation, which we'll come to pretty soon. So let's talk about why we have this this other thermodynamic variable, or thermodynamic function called free energy. Well, it's derived from the second law of thermodynamics. And the second law, we remember, can be used to predict spontaneity. If the change in entropy of the universe is positive, the process, whatever's happening, is going to be spontaneous. You know, in between lectures, I've been thinking about entropy, and I thought, gee, if I just walk along and fall down, probably entropy happening. It's spontaneous, you know, so you can think about that. We've talked about spontaneous things happening. So anytime you observe something spontaneously happening without any outside input, that's entropy. The entropy of the universe is increasing when that happens. And so I want to, let's see, so measurements on the surroundings are seldom made. So we say the entropy of the universe is the entropy change of the system plus the entropy change of the surroundings. Well, the surroundings are huge, right? Our system is pretty compact. It's just a very small part of the universe, while the surroundings are everything else. So measurements on the surroundings are pretty hard to do. For example, the temperature change of the surrounding is hard to do. Because if the system gives up just a little bit of heat, which is going to cause the temperature of the surroundings to increase, well, the surroundings of the whole universe, you can't really measure that. So this limits the use of the second law of thermodynamics. So it would be convenient to have a thermodynamic function that focuses on just the system, and predicts spontaneity of the system, because that's what we're really interested in, is what systems will undergo spontaneous change. And since we're studying chemistry, we're talking about chemistry systems. So before we get on, I want to just go back and remind you that entropy, S, is defined as heat over temperature. So Q is heat, T is temperature. So the entropy of the system is the heat divided by Q divided by T. That's how we defined entropy back earlier in this chapter. So the second law of thermodynamics, delta S universe equals delta S system plus delta S surroundings. We can change delta S surroundings into the heat change of the surroundings divided by the temperature. Okay, so that's the first thing we're going to do. Let me get my marker here. So the delta S surroundings becomes the heat change of the surroundings divided by T, because entropy is Q over T. All right. So we have to go back to my mouse maybe. Let's see. So where does the heat come from that goes into the surroundings? Or where does the heat go to that leaves the surroundings? Well, it goes into the system. And so what we know about the entropy of the system is that if the entropy change of the system occurs at constant pressure, that the heat change is equal to the enthalpy change of the system. Okay, we talked about that previously. You can read your book, it tells about it. And so we can substitute. So what we know is that the heat change of the surroundings comes from the system, but the sign is different. And for the system, the heat change is equal to the enthalpy when the process occurs at constant pressure, which usually it does. So for Q surroundings divided by T, we can substitute minus delta H of the system divided by T. Sign change because the heat change in the system is opposite to the heat change in the surroundings, right? Q surroundings equals minus Q system. Let me write that down. So just to be sure, you've done this. So we have Q, whoops, come on. So Q cis, or sorry, it doesn't matter, Q cis, or I'll say minus Q cis equals Q surroundings, right? All right. So that's where that comes from. And we said that Q cis is delta H of the cis. Now, if we take that, the next step would be to, in this derivation, is to multiply both sides by minus T. So negative T. So minus T here is going to give a plus delta H here, and a minus T delta S here, and a minus T delta S universe over here. So remember that a positive delta S universe is a spontaneous energy change. So here, this whole thing, minus T, or a delta S universe, delta S universe is positive energy change. And now we multiply times the minus T. Well, what the physicist and chemist, it was American chemist, is who Gibbs was. He came up with this free energy equation. So he assigned minus T delta S the symbol delta G. So he just gave that, and that's what we call the, come on, there we go, the delta G. That's what we call Gibbs free energy, or just simply free energy. And so if we substitute the delta G for the minus T delta S, we get delta G plus delta H minus T delta S. And we've done away with the subscript SYS systems because this is for the system. This is for the system, not the universe. But the delta G is equal to minus T delta S of the universe. And so you'll notice the way this equation is set up, that a positive delta S is going to give a negative delta G. So a negative delta G is a spontaneous process. So a process that has a negative delta G will be spontaneous. That's from the definition that delta G equals minus T delta S of the universe. Okay, next slide. I'm going to clear all this stuff that I wrote all over the board. Right there. There we go. So summary of the what free energy is. So the changes in Gibbs free energy, or simply the change of free energy, allows us to predict spontaneity by focusing on the system only. So delta G is a thermodynamic state function. It's derived from enthalpy, which is a thermodynamic state function, and it's derived from entropy, which is also a thermodynamic state function. So that makes delta G also a thermodynamic state function. The sign of delta G indicates if a reaction will be spontaneous or not. So if delta G is less than 0, the reaction is spontaneous in the forward direction. That means, I put in parentheses here, that means that delta S of the universe is greater than 0. If delta G is greater than 0, then the reaction is not spontaneous in the forward direction, and that means delta S universe is less than 0. It comes from this equation up here at the top. This is what we're using to determine whether the free energy, whether a positive or negative free energy is spontaneous or not spontaneous. And so it's derived, the power of the free energy equation comes directly from the second law of thermodynamics. If delta G is equal to 0, the system is at equilibrium. And delta S of the universe is also 0. So let's continue. So let's look at this relationship between delta G, delta H, and delta S. So remember, for spontaneous reactions, one thing we talked about really early on, even before we talked about the second law of thermodynamics, is that many spontaneous reactions occur with a delta H less than 0. So a negative enthalpy seemed to indicate that the reaction would be spontaneous. If you look at the equation for Gibbs free energy, a negative delta H would produce a negative delta G as long as the negative delta H is greater than the minus T delta S. Okay? So we can say, though, a negative delta H contributes to a negative delta G. Also, we know that later, as we start talking about entropy, that processes that seem to produce more microstates or spread out the energy also are spontaneous. And we ended up understanding entropy was the reason for that, and that a change in entropy, or a change in entropy greater than 0, was also associated with spontaneous processes. And you can see if you put a positive delta S in this free energy equation, you have a negative sign in front of that. So minus times a positive delta S is going to give a negative quantity contribution to the free energy. And the negative free energy is spontaneous. Okay, so that's how enthalpy and entropy contribute to spontaneous processes. So any process with a negative delta G is going to be spontaneous. All right, now we're going to look at more details. So note that a reaction can be spontaneous when the delta H is positive or delta S is negative. So if a delta H is positive, if we have a large delta S is positive, we have a large minus contribution from minus T delta S, that's going to make the delta G negative. If the delta S is negative, then this right side of this equation is positive, but a large negative delta G, or delta H, a large negative enthalpy will also produce negative delta G. Note there's a temperature dependence here for the enthalpy part of this equation. So the enthalpy part of this equation has this temperature component, which is very important. Let's continue. We'll be exploring this more in worksheet 24. So here's the table. And on the left side, I've got different signs for delta. This is a qualitative. interpretation of free energy and how a qualitative interpretation of how the different uh, delta H's, enthalpies and entropies will affect the free energy. So in the left-hand column, I have negative delta H, positive delta H, negative delta H, positive delta H, and then opposite that, the delta S, the difference in free energy or an entropy of positive, negative, negative, positive. So you have combinations of enthalpy and entropy with different signs. So how is that going to affect the free energy? So in row one, if we have a negative enthalpy and a positive entropy, that will give us, so we have a negative enthalpy, a positive entropy. Well, the signs of both of these, when we combine them, are going to give us a huge negative value. So the delta G will be negative, and the temperature component at all temperatures. So it doesn't matter what temperature, the minus T delta S is going to be negative because of the positive entropy, and the delta H is negative. So together they make a negative delta G at all temperatures. All right? So this is what we're going to explore. I think you've got the idea by now. So let's look at the second. If we have a positive delta H, well, a positive delta H is not going to help the free energy become negative. But a negative and a negative delta S, negative times negative, is also positive. So we have a positive delta H component, a positive T delta S component, means that not at any temperature is the delta G going to be negative. So a system with a positive delta H and a negative delta S is never going to be spontaneous. The reverse reaction will be spontaneous, but we're talking about forward reactions now. So in the forward reaction, the delta H is positive and the delta S is negative. That will never happen. So not at any temperature. Delta G will be positive under these conditions. So what if we have a negative delta H and a negative delta S? So delta H is negative and delta S is negative. Well, a minus delta S is going to be positive. This is a positive component, so the right side is positive. And let's see, so this side now is positive, and this side is negative. So it looks like we can make the delta G negative if the entropy part of this equation is really small. So how do we make it small? We make it small by keeping the temperature low. So it's negative, the delta G would be negative, the reaction would be spontaneous at low temperature. Now, if we change these, let's change these, and we'll make the delta H component positive. We'll make the T delta S component negative because delta S now is positive. How can we make the entropy or the free energy negative? Well, this side has to be, the entropy side has to be large. So we can make that large by making the temperature high. So the free energy will be negative at high temperature. All right, so that's kind of a qualitative understanding of how enthalpy and entropy and temperatures are going to affect free energy in a chemical reaction. So this is a graphic of what we just went over. So at an entropy greater than 0 and an enthalpy greater than 0, both positive, at very high temperatures, delta G will be 0, and at low temperatures, delta G will be greater than 0. So high temperatures, delta G will be less than 0. Low temperatures, delta G will be greater than 0. So I'm not going to go over it. We just went over this. If you want to come back to this slide later when you're studying, you can look at it and study it a little more. On the right side is a graphic representation of this. And this is showing free energy. So at the top of this slide, in the middle, we have free energy is equal to 0. When free energy is equal to 0, remember that's when the system is at equilibrium. So when the delta G is greater than 0, it's not at equilibrium. So that's actually when delta G is greater than 0, it's a non-spontaneous process. So that's the non-spontaneous region. When delta G is less than 0, it's the spontaneous region. Well, the green situation is where we have a negative delta H and a positive delta S. It's spontaneous at all temperatures. So here's the temperature coordinate at the bottom. So we see this green line at all temperatures, doesn't matter how high temperature we go. The delta G keeps getting more and more negative, and the reaction is spontaneous. If we have a negative delta H and a negative delta S, then at low temperatures down here, the reaction is spontaneous. But as you get up to high temperatures, then it becomes non-spontaneous. The delta G goes greater than 0 because the temperature component, the T delta S, becomes more positive than the delta H. All right, so, and similarly, we could walk through the graphs above that, but I'll let you do that. If you have any questions, come and see me during office hours. All right, so next slide. Oh, there we go. Okay, let's look at the direction of spontaneous change. To calculate the temperature at which the spontaneity of a reaction changes from spontaneous to non-spontaneous. So we said for the conditions where there's a negative delta H and a negative entropy, that at low temperatures, that will be spontaneous, but at high temperatures, it's not. And the opposite, if you have a positive delta H and a positive delta S, those will be spontaneous at high temperatures. So there's a temperature component in those two conditions. So we can calculate the temperature at which the spontaneity changes from spontaneous to non-spontaneous or vice versa. So let's look at our equation. So to find the temperature which delta G is zero, remember delta G is equal to 0 is equilibrium. So nothing's happening there. The reaction is not changing at equilibrium. The amount of products and the amount of reactant stays the same. So if we set delta G equal to 0, we can calculate the temperature at equilibrium where these, by just taking delta H divided by delta S, where these, where it's going to change from spontaneous to non-spontaneous. So if the delta H is positive and the delta HS is negative, this temperature, the temperature of spontaneity, is going to be greater than the temperature of equilibrium. When delta H is negative and delta S is negative, remember this, in this situation, the spontaneity is going to occur at the lowest temperature, at a lower temperature. So that means the temperature of spontaneity is going to be less than the temperature of at equilibrium. All right, so we're going to work on these. I think worksheet, one of the worksheets also has us, worksheet 25, we'll be doing these calculations. Okay. So although the change in Gibbs free energy is valid under all conditions, we will most often apply it at standard conditions. So we can there's a scale of standard entropies of, or excuse me, free energies of formation for the different compounds. So again, just to review, standard conditions are 1 atmosphere, 1 mole, and 298 K for 25 C. And under standard conditions, we put a little superscript 0. So the free energy change, the standard free energy change is going to equal to the standard enthalpy change minus temperature times the standard entropy. Now, when we do these calculations, which we'll be doing in worksheet 25, you have to pay attention to the joules versus kilojoules. So Free energy is in kilojoules per mole. Entropy or enthalpy is in kilojoules per mole. That entropy is in kilojoules, or excuse me, joules, only joules per mole Kelvin. Okay, so entropy is joules per mole Kelvin, enthalpy is kilojoules per mole, and free energy is kilojoules per mole. So we're doing these equations. You have to make sure you keep your energy units straight. Doesn't matter whether you use kilojoules or joules, just it has to be consistent when you're doing these calculations. So the standard free energy of formation for a compound is defined as the free energy change for the formation of 1 mole of substance from its elements in their standard state. We talked about the standard state before. This is analogous to the enthalpy of formation discussed in chapter 5. And an example for the free energy formation, this would be for water. So 1 mole of water, the free energy of formation is minus 237.2 kilojoules per mole. The free energy of formation for the elements is 0. So the delta G F for water then is this. So they're formed from the elements. So we're talking about forming compounds from the elements, not from another reaction. So let's look at another use for free energy is to calculate the free energies of reactions from the free energies of formations of the reactants and the products. And the equation here is that the free energy change for a reaction is equal to the sum of the free energies of formations of the reactants minus the sum of the free, the sum of the free energies of formations of the products minus the sum of the free energies of formation of the reactants. So we have free energy of C plus D minus the free energy of A plus B. So we can summarize that the free energy, the standard free energy of a reaction, the delta G0 for a reaction or process is the sum of the free energies of formation of the products minus the sum of the free energies of formation of the reactants. And as I mentioned previously, the free energy of formation for any element is 0. So this is also called Hess's law, which we learned previously when we talked about entropies and enthalpies. So up to this point, we have been talking mostly about free energies of processes, but we can also talk about free energies when substances are 1 molar concentration. So we talk about 1 mole, but we can do free 1 molar concentrations and use pressures, because pressures are related to concentrations also. We learned that for gases. So there's a general equation that allows us to relate the free energy change to the standard free energy reaction plus the RT log Q. Remember, Q is the reaction quotient. So this is another important equation to relate the free energy changes that occur, the change in free energy at under non-standard conditions. So delta G equals delta G0 plus RT log Q. Again, this is how we calculate the delta G under conditions that are not standard. And a few things here. T is temperature in K always. R is 8.314 joules per mole per K, or R is 008314 kilojoules per mole K. Notice that the units of R are the same units as entropy. So we've talked about, so far, this chapter, the relationship between free energy change and the spontaneity of a reaction. So remember, delta G must be 0 for a spontaneous reaction. But another measure of reaction spontaneously that we learned in the last few chapters 13, 14, and 15 is the equilibrium constant. And when we talk about spontaneity, we're talking about processes that are going to favor the products over the reactants. So for spontaneous reaction, K would be greater than 1. Remember, a K greater than 1 means that the products are favored over the reactants. If K is less than 1, then we know that the reactants are going to be favored over the products. And if reactants are favored over products, it means that reaction isn't going to occur. So we can determine what the equilibrium constant is from the standard free energy change of reaction. If we look back at our equation relating a change in free energy other than at standard conditions, delta G equals delta G naught plus RT log Q. Well, we know that at equilibrium, log Q is log K. So we can, and at log K, delta G is 0. So we can set 0 equals delta G naught, or standard delta G, plus RT log K, and we can calculate the equilibrium constant in terms of the standard free energy change for a process. Another important equation that we're going to use in worksheet 24. So this relationship between standard free energy change and equilibrium constant holds for all equilibrium constant we've discussed so far. That would be Kc, which is equilibrium constant in terms of concentrations, equilibrium constant in terms of pressure, equilibrium constants for acids, equilibrium constants for bases, the equilibrium constant for water, and the equilibrium constants for salts, partially soluble salts. So this graph kind of shows a graphic representation of what we were talking about before. So in figure 1 on the left side here, we've got a process that has a delta G naught, a standard entropy change less than 0. We know that's going to be spontaneous. We know that means it's going to change. We start with the reactants. It's going to change as the reaction progress to products spontaneously. So the energy, the free energy of the products is less than the free energy of the reactants. That's going to change spontaneously towards products. The minimum here is the equilibrium point. That's where Q equals K. Q equals K. And K is greater than 1 because the equilibrium falls towards products. So when the system's at equilibrium, we're going to have mostly products. That's what this means. This is the progress of the reaction. The reaction is going to progress mostly towards products. Okay, let's look at another situation where delta G, standard delta G is 0. That means the system is at equilibrium. That means Q is equal to K. And if delta G is 0, it means the free energies of the reactants and the products are the same. So there's not going to be any change. Okay, so if delta G is 0, the concentration of the products over the reactants is going to be equal to 1. K is equal to 1. And the equilibrium is going to lie equal distance along the reaction between reactants and products. If you start over here on the left side, then Q is less than K. It means we have too many products, and the reaction will proceed forward until we reach the equilibrium point and stop. If you start over here where Q is greater than K, then the equilibrium will progress, towards the equilibrium point, more products will be formed. We know if Q is greater than K, that's going to cause the formation of more reactants. If Q is less than K, it's going to cause the formation of more products. But when the concentrations become equal to K, when Q is equal to K, the change stops because system's at equilibrium. Over on the right side, delta G is greater than K. It means that if you start with reactants, that reaction might progress a little bit towards products, but not very far. And so the equilibrium is going to lie on the side where there's mostly reactants. So we're closer, the equilibrium point on this reaction curve, reaction profile, is closer to the products than it is, is closer to the reactants than it is to the products. So starting with the reactants, the reaction just doesn't go very far. It doesn't produce very many products. Maybe a little bit until equilibrium is attained, but the equilibrium favors reactants because K is less than 1. Okay, as with enthalpy, free energy changes for reactions are additive. So if you remember, you used Hess's law. If you add two reactions together, you would add their enthalpies together. If you subtract two reactions, you would subtract their enthalpies. And so also keep in mind that if the reaction is reversed, then the sign of the delta G will also be reversed. So again, this is another application of Hess's law. Another factor, if the reaction is multiplied by a factor of n, then the delta G is also multiplied by a factor of n. So all those rules that we used for enthalpy and Hess's law, combining reactions, subtracting reactions, reverses reactions, multiplying reactions by an integer value, all apply to free energy also. So in summary, here are a few of the equations, formulas that we went over. So so free energy equals delta H minus T delta S. Standard free energy equals standard entropy, or excuse me, standard enthalpy minus temperature times standard entropy. Also, if you want to find the free energy of a standard free energy of a reaction, we would take the sum of the free energies of formations of the products minus the sums of free energies of formation of the reactants. We want to calculate the free energy at under conditions of temperature that's different from standard. We would use a equation where delta G standard plus RT log Q, where log Q would be the concentrations or the pressures. And lastly, if we want to calculate the equilibrium constant, we can do that from the standard free energy of the process. And all of these equations are going to be used in worksheets 24 and 25. So let's get to those worksheets. So I'm going to minimize this slideshow, and I'm going to maximize the worksheet. So here's the worksheet. So I hope you can see that. I think so. I'll maximize it here. So this worksheet has to do with, it's worksheet 24. We're going to look at qualitatively what happens to a process. And in question 1, brighten this up a little bit, focus it. It says for a spontaneous process, there's a, that has the free energy statement at the top. Delta H minus T delta S is less than 0. For a non-spontaneous process, delta H minus T delta S would be greater than 0. So the value for this reaction, N2O4 going to 2NO2, delta S is positive. Delta H is also positive. So what do we know about if the temperature is very low, what do you expect do you expect the reaction to be spontaneous? Well, if delta S is positive, so we have our overall reaction is delta H minus T delta S. Okay, this is equal to delta G. So we have a positive delta S, which makes this negative value, and we have a positive delta H. So that means in order for delta G to be negative, the minus T delta S has to be. So this would occur it would be spontaneous at high temperatures. So the question is, if the temperature is very low, do you expect the reaction to be spontaneous? And the answer is no, not spontaneous. I'll put not spontaneous. And the reason is because at low T, delta H minus T delta S would be greater than 0 because the positive delta H is going to be most important. All right, so that's how you think or solve a question like that. I'll let you do number 2. So I've circled that. This is for you to do. Okay, let's go to number 3. And the circle ones are the ones I want you to do. And so I will do number B. So I want you to do this one, A and C. And I will do B and D down here. So let's look at these. So delta H is, for B, we have 3 oxygens going to 2 ozones. So delta H is positive and delta S is negative. So if delta H is positive and delta S is negative, what's that going to do to our delta H minus T delta S? Or delta H minus T delta S looks to me like it's always greater than 0. So the answer here, let's see, this is always greater than 0. So the answer here is no T. No T. No T will this be spontaneous. All right, I'll let you do, like I said, A and C, and I will do D. Let's look at D. For delta H, for D, delta H is positive, and S is positive. And so this would be negative when, let me write this again. Now, you always have to use this as reference, delta H minus T delta S. So the delta S is positive, the delta H is positive. We want this side to be negative, so that's going to happen when T is high. So this would be high T. Okay, so you guys do the other ones on that. So let's flip the page and look at these next questions. So this gives an explanation of free energy, which we went over in the lecture, the PowerPoint lecture. So I'm going to skip that, but you can read that if you want. It'll reinforce what we've already covered. But at the end of this, it talks about it's talking about equilibrium. So if delta G 0 plus RT log K equals 0, this is what happens at equilibrium. Then delta G0 equals minus RT log K. So we can calculate the standard free energy change from the equilibrium constant. And that's what is asked for in question 4. So I'm going to do question 4. I'm going to do question 4. Let me underline that. And I want you guys to do question 5. So both of these are the same. I mean, they're not the same problem, but they use this equation. So let me do question 4. And get my little, I've done this already, so I'm getting my answer here. I'll just rewrite it here. So we're going to use delta G, standard delta G is equal to minus RT log K. And the question is, what is the equilibrium constant? So we have to rearrange this to solve for K. So I'm going to rearrange it. So I get log K is equal to delta G, standard delta G, or the delta G, the free energy, divided by minus RT. So the free energy is minus 9.2 kilojoules per mole. So I'm going to change that, though, to joules per mole. Remember our the little comment previously, you have to pay attention to joules and kilojoules. Since R, I like to use R in joules per mole K and not kilojoules. So I'm going to change delta G to joules. So this is minus 9,200 joules per mole. And I can divide this by minus R, which is 8.31 joules per mole per K. This is all in parentheses, times 298. So when I do that, what I end up with is 3.72. Now over here, what I have to do, this is log K, remember. So log K equals 3.72. Let me sharpen my pencil a little bit. So K is going to equal E to 3.72. And if we do that on the calculator, K turns out to be 41, which makes sense. K is greater than 1. We know that delta G is negative, so spontaneous reaction is going to favor product. A K equal to 41 favors product. All right, so problem 5 is using the same equation, but in this case, it's for hydrofluoric acid. The pKa is 3.2. So the first step, I'll give you a tip here, is to change the pKa into the Ka. Okay, and then the Ka you can plug right into this equation to calculate the delta G. All right, and remember, keep in mind a check on whether your work, you're doing it right or not. If the K is greater than 1, the delta G should end up negative. If the K is less than 1, the delta G should be positive. All right, so that's the end of worksheet 24. Let's go to the next worksheet, 25. So worksheet 25 says chemical reactions with a positive delta G are non-spontaneous. However, reactions such as this are carried out by routinely coupling the non-spontaneous reaction with a highly spontaneous reaction. The reaction below creates the industrially important chemical quicklime at a rate of 70 million tons per year in the US. So the enthalpy of formation, so it's calcium carbonate, and calcium carbonate is marble. One form of calcium carbonate is marble. In this process, it's limestone. And so from the limestone, they're making this substance called quicklime, calcium oxide, which is used in cement. It's a major product in cement. But the delta G for this reaction is positive. So I think the first problem 1, I'm going to do this whole worksheet, I think. Let me see. Am I going to have you do this second part? Yeah, I'm going to do the whole thing. These are all linked. So there's 3 questions on 25, and they're all linked. So use the enthalpies of formation and the standard entropies at 25 degrees to determine the standard Gibbs free energy for the change in this reaction. So the standard enthalpies of formation and the standard entropies of formation are shown here, the standard entropies. And so remember, previously we could do, the equation we're going to use in all this is delta G equals delta H minus T delta S. So right away, it's at 25 degrees. So let's write that down. T is going to equal 298. It has to be in Kelvin. It's 298 K. Okay, so I'm going to write that down. There's a couple ways we can do this. So first of all, we could find the delta G's of formation, the standard free entropies of formation for each of these. So let me write these down. We could do that. Let me zoom in here. So if you look at that, we can calculate those by just doing the delta H of formation minus the T delta S. So we can get those for each of those. And if we do that, let me see, I have this one. I've done this before too. So if we do that, we get this for the delta G's. We get this, the delta G of formation for the calcium carbonate is minus 1, 2, 3, 4 kilojoules. The calcium oxide, the delta G for calcium oxide is minus 6, 4, 7 kilojoules. And the delta F, or the delta G formation for CO2 is minus 457 kilojoules. So then we would use our Hess's law, which would be the products, sum of the products minus sum of the reactants. So we're going to do the sum of the products, which are CO2 and CO2, CaO. These are the products, right? These are the products here. Limestone is the reactant. So the sum of the products minus the sum of the reactants, I'll put R. And when we do that, we get 129, about 130 kilojoules. Sum of the reactants minus the sum of the products, because 130 kilojoules. So that matches, this is not a spontaneous reaction because the delta G is positive. So the delta G for the reaction then is 130 kilojoules. So the next, that's one way to do it. There's another way to do it. Maybe I'll point this out. Maybe you can do it the other way. So the other way, instead of determining the delta G's of formation, what you can do is use the, you can find the delta H's, the delta H, the standard enthalpy of this reaction, and the entropy change for the reaction by taking the sum of the products minus the reactant for both the entropy, the enthalpy, and the entropy, and then calculating the free energy change by taking the delta H of that minus T delta S. So what you would do, the alternate way would be the delta H of the reaction, standard free is the sum of the delta H product minus some delta H reactant. Step 2 is the delta S reaction is going to equal the sum, the delta S product, or the S product, not the delta S, it's just the S product. Let me change that, because that's what we're given here. The delta S for the reaction is the entropies of the product minus the entropies of the reactant. Then the third step is the overall free energy change for the reaction is the delta H for the reaction minus the T delta S for the reaction. So you guys do that one. I want you to do this, okay? I showed you how to do it one way by figuring out the free energy change of formation for the reaction to the products and figuring that out. And this is the second way you can do it, is to find the enthalpy, the entropy, and then calculate the free energy change for the reaction from those. It should come out the same. So to check, what you should be looking for is a value of 130 kilojoules. All right. Let's go on. So determine the temperature with this reaction changes from non-spontaneous to spontaneous. So in this case, we have a positive delta H. What's our delta H? I guess you'd have to figure this out. I'm not sure if we have a positive delta H and a negative. So I think what we end up with, I think we have a positive delta H and a positive delta S. So they're both positive. And when they're both positive, we know that this reaction is going to be spontaneous at a really high temperature. Okay, so you have to figure this out. If both of these are positive, it means it's going to be high temperature. And oh, I guess we have to know those. The delta H and the delta S for the reactions do this part too. We have to know this because we have the delta G for the reaction. I already wrote this down, is going to equal the delta H for the reaction minus T delta S standard for the reaction. And we're going to arrange this so this is going to equal 0 at equilibrium. And so our T is going to be our delta H for the reaction divided by, oops, you can't even see that. I'm writing all this stuff down. You can't see it. Divided by delta S for the reaction. So that's with the temperature at equilibrium. So I'm going to put this equilibrium temperature. I'm going to put E back here. So what you need to do is calculate the temperature of spontaneity. And it's going to be either greater than or less than. So up here, I'll let you do this one. I want you guys to figure out this one. So in 1 and 2, you figure out the delta H for the reaction and the delta S for the reaction. You plug those in here, set it equal to 0, and calculate what temperature is at equilibrium. So it's not going to be 298. Because the 298 occurred when delta G was equal to, well, whatever this delta G is, whatever, it's supposed to be 130. So when you do this, you should get the delta G is 130. But when we change the delta G 0, the standard delta G, standard free energy to 0, the temperature is going to be different. And that's the temperature you want to find out. And then determine whether spontaneity will be greater or less than that temperature. All right, you guys do that one. So let's do this next one. So one way to generate each or such a temperature as to heat the reaction by burning coal. While the actual combustion of coal is more complicated, the reaction below simulates coal burning. Use the thermodynamic data at 25 degrees. So T, again, remember our temperatures always have to be in Kelvin. So that's 298 Kelvin. To determine the standard free energy change for this reaction. So here's our reaction. Carbon plus oxygen gives CO2. And the standard free energy change for this, so it's delta G for this carbon burning reaction is going to be the sum of the products, which is CO2, times the coefficient, which is 1. So it's 1 mole times minus 394.4 kilojoules per mole. Minus the free energies of formation for the reactants, which are elements, so it's minus 0. So the delta G 0 is going to equal minus 394.4 kilojoules. Now the question is, so that's number 2. That was pretty easy. The last one says, using Hess's law and the standard free energies of reaction, determine the overall free energy for the coupled reactions. So what are the coupled reactions? Coupled reactions mean they're both going on at the same time. So we want to do this forward reaction, carbon, so we're going to burn coal. So the one reaction is this one, carbon solid plus oxygen gas produces CO2 gas. And then the other reaction is the one up above, which is calcium oxide. Oh wait, not calcium oxide, calcium carbonate. Let me fix that. Calcium carbonate plus just heating calcium carbonate solid going to CO2 gas plus CaO solid. And we're going to add those together. And when we add those together, here we go, let's add those together. We get our net reaction, which is CaCO3 solid plus carbon solid plus oxygen gas going to produce 2 carbon dioxides, gas plus calcium oxide. That's what we're after, the calcium oxide. That's our product. Okay, so what's the delta G for that reaction? Well, we added those together, so the delta G is going to be the sum of the delta G's for each of those. So we know the delta G's here, so I'm just going to put delta G up here for our 2 reactions. Delta G didn't come out that great. Maybe if I used a pen, it'd be better. But then I couldn't erase, so I'm going to stick with a pencil. So delta G for the carbon burning is minus 394.4 kilojoules. And way up above in number 1, we calculated the delta G for the limestone, or the calcium carbonate going to calcium oxide is 130 kilojoules. So we have 130 for the forward reaction. And the answer then is, we're just going to add those 2 together. We'll move this over a little bit. We'll move this. We're going to add those together. When we add those together, we end up with about 2 minus 264 kilojoules. And that's our answer. So for the coupled reaction, the free energy change is minus 264 kilojoules, which means that that would be spontaneous. That should work. All right, so that's it. A little bit on this last one. This is Hess's law. Remember, if we combine two reactions, but we had to flip one of them. So if we did this backwards, we'd change the sign of the delta G. So if you write the reverse reaction, the sign of the delta G changes. And that's it. So that's the end of chapter 16.4 and the end of chapter 16. And so I'll have office hours on Monday. If you have any questions, just pop in. So I'm going to stop the share and stop the recording. And I will see you later. Bye now.